Welcome! In this session, we'll tackle an exciting graph-based problem, most stones removed with same row or column. We'll explore the intuition, approaches, and key concepts to solve this efficiently. Let's dive in. In this problem, we are given an array of stones, where each stone is represented by its coordinates on a 2D plane. For example, a stone at position x_i, y_i is represented as x_i, y_i. The key idea here is that stones are considered connected if they share either the same row or the same column. Now, a stone can only be removed if it is connected to another stone. Your goal is to remove as many stones as possible, but you must ensure that at least one stone remains in each connected group. The output will be the maximum number of stones that can be removed while satisfying this condition. The input is given as a list of coordinate pairs for the stones, and the output is a single integer indicating the maximum number of stones that can be removed. Let's look at an example to understand this better. Suppose we are given the input stones equals 0, 0, 0, 1, 1, 0, 1, 2, 2, 1, 2, 2. The output in this case is 5. Here's why: the stones form one large connected group because all the stones are either in the same row or the same column as another stone. For instance, the stones at 0, 0, and 0, 1 are in the same row, while the stones at 0, 0, and 1, 0 are in the same column. By carefully removing stones, we can leave just one stone in this connected group and remove the other 5. This maximizes the number of stones removed while preserving the connected group requirement. Now, consider another example. If the input is stones equals 0, 0, 0, 2, 1, 1, 2, 0, 2, 2, the output is 3. In this case, the stones form two separate connected groups. Group 1 includes stones like 0, 0, and 2, 0, which are in the same column, while Group 2 contains stones like 0, 2, and 2, 2, which are also in the same column. For each group, we can remove stones until only one stone remains in that group. By doing this, we can remove a total of 3 stones while ensuring that one stone remains in each connected group. Finally, if there's just one stone, as in the input stones equals 0, 0, the output is 0, because there are no other stones to connect to or remove. Now let's review the constraints and edge cases for this problem. The number of stones can range from 1 to 1000, and the coordinates of each stone are non-negative integers less than 10,000. Additionally, no two stones will occupy the same position. As for edge cases, consider when there's only one stone. In that scenario, no stones can be removed since there are no connections. Another edge case is when all stones are completely isolated, meaning no two stones share a row or column. In this situation, no stones can be removed either. Finally, it's crucial to ensure that the solution handles large inputs efficiently, given the constraints of up to 1000 stones. This means the algorithm needs to scale well and execute within a reasonable timeframe, even for the upper limits of input size. To start with, let's consider the brute force approach. The basic idea here is to repeatedly simulate the process of removing stones. You would check all pairs of stones to see if they share the same row or column, and then remove connected stones one by one. This process would continue until no more stones can be removed. While this approach is straightforward and easy to conceptualize, it comes with a significant downside. The complexity is quite high, n squared, in the worst case due to the need to check all pairs of stones repeatedly. Additionally, managing the removal process manually is inefficient. This makes the brute force strategy impractical for larger inputs, as the computational cost grows quickly with the number of stones. The trade-off here is simplicity at the expense of performance, especially for larger datasets. Now, let's explore a more structured alternative, the graph-based approach using either DFS or BFS. Here, we model the problem as a graph where each stone represents a node, and an edge exists between two nodes if the stones lie in the same row or column. The key insight is that this reduces the problem to finding the total number of connected components in the graph. The maximum number of stones that can be removed is simply the total number of stones minus the number of connected components. To implement this, you would first construct the graph by connecting nodes that share a row or column. Then, using DFS or BFS, you traverse the graph to count the connected components. While this approach avoids the inefficiencies of brute force, the graph construction itself can still be costly. Specifically, building the graph has a complexity of O(n) squared, in the worst case, though the traversal is more efficient at O(n). It's a step forward in structure and clarity, but for very large inputs, the graph construction overhead could still be a bottleneck. To address the limitations of graph construction, we turn to the union find approach. This method eliminates the need to explicitly build the graph by using a disjoint set data structure to group stones into connected components. Here's how it works: each stone belongs to both a row and a column, and we treat these as distinct entities. Using a unique encoding, we can union the row and column for each stone, effectively grouping them. After processing all stones, the number of unique connected components is counted. Finally, the result is obtained by subtracting the number of connected components from the total number of stones. This approach is highly efficient, with union find operations running in nearly constant time due to path compression and union by rank. The overall complexity is O(n) alpha n, where alpha n is the inverse Ackermann function, which grows extremely slowly, making the approach effectively linear in practice. This efficiency, combined with its scalability, makes union find an excellent choice for this problem. Ultimately, we selected the union find approach as the optimal solution. The main reason is its efficiency and scalability, particularly for large inputs. The core insight lies in reducing the problem to counting connected components in a graph, which union find handles in a highly optimized manner. Unlike brute force, it avoids repetitive and unnecessary computations. Compared to DFS or BFS, it bypasses the need to explicitly construct the graph, saving both time and memory. The breakthrough came from recognizing that rows and columns could be treated as nodes in a graph, allowing union find to merge components dynamically and efficiently. By focusing on grouping stones rather than simulating their removal, we achieve both clarity and performance. This balance of simplicity, efficiency, and scalability makes the union find approach the best strategy for solving this problem effectively. In this problem, we're given a set of stones on a 2D grid, each defined by unique coordinates. The goal is to remove as many stones as possible, with the rule that a stone can only be removed if there's another stone in the same row or column. The key challenge is to determine the maximum number of stones that can be removed. To solve this, we can model the problem as a graph where each stone is a node, and nodes are connected if they share a row or column. Using this graph-based approach, the task boils down to finding the number of connected components. Each connected component can leave behind exactly one stone, so the maximum number of removable stones is the total number of stones minus the number of connected components. To efficiently solve this, we'll use the union find data structure. First, we'll map the stones into a graph representation. Each stone becomes a node, and to handle the row and column connections, we'll shift the column indices by a large constant, such as 10,000. This ensures that row indices and column indices operate in separate spaces, avoiding any confusion during graph construction. The next step is to initialize the union find data structure. Instead of using an array for parent pointers, which would be inefficient for large or non-contiguous coordinate values, we use a dictionary. This allows us to handle the potentially large range of coordinates without allocating excessive space. To keep our operations efficient, we'll implement path compression and union by rank. Once the data structure is ready, we process each stone. For every stone at coordinates x, y, we compute its unique identifiers for the row and column, with the column index adjusted by the offset. Using these identifiers, we perform union operations to connect the row and column of the stone. After processing all the stones, we then count the number of unique connected components by identifying the unique roots in the union find structure. Since each connected component corresponds to one stone that must remain, the maximum number of removable stones is calculated by subtracting the number of connected components from the total number of stones. This approach has several important insights. First, the efficiency of union find is critical to handling large inputs. With path compression and union by rank, each operation, find or union, takes nearly constant time, making the algorithm scalable. Second, the coordinate mapping step, where we shift column indices by a large offset, is crucial. This ensures that row and column indices don't interfere with each other in the union find structure, effectively treating them as nodes in a single graph. Finally, the graph perspective simplifies the problem significantly. Instead of trying to manually simulate the process of removing stones, we focus purely on the structure of connected components, which provides a clear and efficient solution to the task. The union-find data structure is at the heart of this solution. It allows us to efficiently group stones into connected components. The key operations here are find, which retrieves the root of a node while applying path compression to flatten the structure, and union, which merges two components, using union by rank to keep the tree balanced. These features ensure that the data structure remains efficient. In terms of storage, we use a dictionary to manage parent pointers and ranks, which is space efficient given the potentially large range of stone coordinates. The time complexity of the algorithm is O, n asterisk alpha, n, where n is the number of stones and alpha, n, is the extremely slow-growing inverse Ackermann function, making it almost constant in practice. The space complexity is O, n, for storing the union-find structure, making this approach both time and space efficient for the problem at hand. Let's walk through an example to solidify our understanding. Imagine the input stones are placed at coordinates 0, 0, 0, 1, 1, 0, 1, 2, 2, 2, and 2, 3. For each stone, we perform union operations to connect its row and column. For instance, for the stone at 0, 0, we union row 0 with column 10,000. Similarly, for 0, 1, we union row 0 with column 10,001, and so on for the other stones. After processing all the stones, we determine the number of connected components by counting the unique roots in the union-find structure. Suppose we find 3 connected components. With 6 stones in total, the maximum number of removable stones is calculated as 6 minus 3, which equals 3. This example illustrates how the algorithm groups stones into components and computes the result efficiently. To optimize this solution further, we leverage techniques like path compression and union by rank. Path compression ensures that the union-find structure remains shallow by directly connecting nodes to their root, improving the efficiency of subsequent find operations. Union by rank balances the tree structure during union operations, minimizing its height and keeping the algorithm efficient. Additionally, the offset mapping of column indices simplifies the handling of row and column relationships, avoiding unnecessary complications. It's also important to consider edge cases. For instance, if there's only one stone, no removals are possible, so the output is 0. If all stones lie in a single line, only one connected component forms, and the output is the total stones minus 1. Finally, if the stones are completely disconnected, each forms its own component, and no stones can be removed. These scenarios demonstrate the robustness of the algorithm in handling different configurations of stones. This implementation solves the problem using the union find, or disjoint set union, algorithm. The stones are treated as nodes in a graph, where 2 stones are connected if they share the same row or column. Each stone's row and column are mapped uniquely using the row index as is and the negative of the column index, e.g., y. This ensures that row and column indices are treated distinctly. The find function is used to determine the root of a node, with path compression to optimize the operation. The union function connects 2 nodes by linking their roots. For every stone, we union its row and column indices. After processing all stones, we calculate the number of unique connected components by applying find to all nodes in the parent dictionary. The maximum number of stones that can be removed is then the total number of stones minus the number of connected components. This approach ensures an efficient solution with nearly constant time operations for union and find. Here, we start implementing the solution to the problem using Java. First, we import the necessary packages, including java.util*, which will allow us to use data structures such as hashmap and hashset. We then define the solution class and the removeStones method, which takes a 2D array of stones as input. Inside this method, we declare a parent hashmap to represent the union-find data structure, where each key represents a node, and its value represents the node's parent. Next, we define the find function, which is used to locate the root of a given node. This function incorporates path compression to optimize the union find structure, ensuring that future queries are faster by directly linking nodes to their root. After that, we define the union function, which merges 2 sets by connecting their roots. If the roots of 2 nodes are different, we update one root to point to the other, effectively merging the sets. Finally, we begin initializing the parent map by iterating through the stones. For each stone, we extract its row index X and column index Y. To avoid conflicts between rows and columns in the union-find structure, we use the bitwise not operator on Y, differentiating rows from columns in the map. Continuing the implementation, for each stone, we check if its row index X and the transformed column index Y are already present in the parent map. If not, we initialize them in the map with themselves as their own parents. We then call the union function to connect the row and column indices of the current stone, essentially linking them in the union-find structure. Once all stones are processed, we calculate the number of unique connected components by iterating over the keys in the parent map. For each key, we use the find function to determine its root and add it to a hash set called unique roots. The size of this set represents the number of unique connected components. Finally, we return the total number of stones minus the size of unique roots, which gives the maximum number of stones that can be removed while leaving at least one stone in each connected component. This completes the implementation of the solution. In this example, we have 6 stones placed at the given coordinates. The goal is to remove as many stones as possible while ensuring that at least one stone remains in each connected group of stones. To solve this, we use the union find algorithm. First, we initialize an empty dictionary called parent to track the connected components. We also define helper functions find and union to perform the union find operations. When processing each stone, we treat the row and column as distinct nodes by using the row number directly and the negative of the column number. For the first stone at 0, 0, we add row 0 and column -1 to the parent dictionary and connect them using the union function. This marks the row and column as part of the same connected component. Next, for the stone at 0, 1, we add column -2 to the parent dictionary and connect row 0 to column -2, linking this stone to the existing component. For the stone at 1, 0, we add row 1 to the dictionary and connect it to column -1, creating a new connection that links row 1 to the component containing column -1. For the stone at 1, 2, we add column -3 to the dictionary and connect row 1 to column -3. Similarly, for the stone at 2, 2, we add row 2 to the dictionary and connect it to column -3, ensuring that row 2 becomes part of the component containing column -3. Finally, for the stone at 2, 3, column -4 is added, and row 2 is connected to it. At the end of this step, all rows and columns corresponding to stones are part of connected components, as defined by the parent dictionary. To determine the number of stones that can be removed, we count the number of unique connected components. Using the find function, we identify the roots of each component. Here, we find 2 unique roots, 0 and 2, representing 2 connected components. Since there are 6 stones in total and 2 components, the maximum number of stones that can be removed is 6 minus 2, which equals 4. This gives us the final output of 4. In the second example, we now examine a simpler case with 3 stones placed at 0, 0, 1, 1, and 2, 2. Each stone is isolated, meaning no stone shares a row or column with another. Let's go through the steps to confirm this. Starting with the initialization step, we again create an empty parent dictionary. For the first stone at 0, 0, we add row 0 and column -1 to the dictionary and connect them. For the stone at 1, 1, we add row 1 and column -2 to the dictionary and connect them. Finally, for the stone at 2, 2, row 2 and column -3 are added, and they are connected as well. At this point, each stone has its own distinct connected component because no row or column is shared between any 2 stones. To count the number of unique connected components, we use the find function, which identifies 3 distinct roots, 0, 1, and 2. This indicates that there are 3 separate components, 1 for each stone. Since we cannot remove any stones without breaking these components, the maximum number of stones that can be removed is 3 minus 3, which equals 0. The final output for this example is 0. Now, let's consider the third example, where the stones at 0, 1, 1, 0, and 1, 1 form a connected group. We begin by initializing the parent dictionary once again. For the first stone at 0, 1, we add row 0 and column -2 to the dictionary and connect them. For the stone at 1, 0, we add row 1 and column -1 to the dictionary and connect them as well. Finally, for the stone at 1, 1, we connect row 1, which already exists in the dictionary, to column -2. This links all three stones into a single connected component. Using the find function, we determine that there is only one unique root, indicating a single connected component. Since there are 3 stones in one component, we can remove 3 minus 1, or 2 stones, leaving just 1 stone in the connected group. The final output for this example is 2. To analyze the time complexity of this solution, we start with the union find operations. For each stone in the input list, we perform a union operation. A union operation involves 2 find operations and potentially a merge operation. Thanks to path compression, the amortized time complexity of each find or union operation is O, alpha, n, where alpha, n, is the inverse Ackermann function. This function grows so slowly that, for all practical purposes, it can be treated as nearly constant. Since we perform a union operation for each of the n stones, this part of the algorithm contributes a total of O, n asterisk alpha, n, to the time complexity. Additionally, once all the stones have been processed, we determine the number of unique roots by performing a find operation on each node stored in the parent dictionary. With at most 2 n nodes in the parent dictionary, 1 for each stone's row and 1 for its column, this step adds another O, n asterisk alpha, n, to the complexity. Combining these, the overall time complexity of the algorithm is O, n asterisk alpha, n, which is very efficient. Next, let's examine the space complexity of the solution. The primary contributor here is the parent dictionary, which is used to store the parent relationships for the union find data structure. Since each stone corresponds to a unique row and column, the parent dictionary can have at most 2 n entries, 1 for each row and 1 for each column, resulting in a space requirement of O, 2n, which simplifies to O, n. Additionally, the find function in the union find algorithm uses recursion, and the depth of this recursion is proportional to the number of nodes. However, due to path compression, the recursion depth is reduced to O, alpha, n, which is negligible for practical purposes. Other auxiliary data structures, such as temporary sets, also require O, n, space. Therefore, the total space complexity of the solution is O, n, making it highly space efficient. Now let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, all the stones are already part of the same connected component, meaning that union operations require minimal path compression. Even in this scenario, the time complexity remains O, n asterisk alpha, n, due to the union find operations, as alpha, n, is nearly constant. In the average case, the union find structure efficiently handles merges, ensuring that the time complexity stays O, n asterisk alpha, n. In the worst case, each stone initially forms its own connected component, requiring the union find structure to perform merges for all stones. Despite this, the efficiency of path compression ensures that the time complexity does not exceed O, n asterisk alpha, n. When we compare this to a brute force approach, which would involve checking connections between all pairs of stones and result in O, n squared, time complexity, it's clear that the optimized union find solution is significantly faster and far more scalable for large inputs. Finally, let's consider the mathematical justification for the efficiency of this algorithm. The union find data structure ensures that each find or union operation is performed in O, alpha, n, time, where alpha, n, grows slower than any logarithmic function. For practical input sizes, this growth is so slow that alpha, n, can be treated as a constant. With at most 2 n nodes to process, 1 for each stone's row and column, the total number of operations scales proportionally with the number of stones, resulting in an overall time complexity of O, n asterisk alpha, n. This combination of nearly constant time operations and linear scaling ensures that the algorithm is both time and space efficient. In conclusion, this approach is well suited for handling large input sizes and is a significant improvement over the brute force alternatives, which are far less efficient. When solving this problem, there are several common mistakes to be aware of. First, it's crucial to fully understand the problem constraints. For example, the grid could have up to 10,000 stones, and if you misunderstand these limits, you might accidentally create solutions that are too slow or overly complex. A second issue is overcomplicating the brute force approach. While brute force is inherently inefficient, it should be simple and direct. Adding unnecessary data structures or extra checks can make debugging harder, and you might lose clarity in your solution. Another frequent mistake is incorrectly handling connectivity. Since this problem revolves around grouping stones by shared rows or columns, failing to properly account for all connected stones can lead to incorrect results. Finally, edge cases are often ignored, such as grids with just one stone, all stones in the same row or column, or cases with disconnected components. Failing to account for these edge cases can cause unexpected failures, so testing thoroughly is essential. Another common mistake is implementing an inefficient union find. Without path compression or union by rank, the performance could degrade to O(n)(, which is far from optimal. On the other hand, understanding the key patterns in problems like this can help you develop a solid approach. Problems involving grids and connectivity often boil down to graph-based techniques like DFS, BFS, or union find. Identifying connected components is a recurring theme, and recognizing this pattern early can guide you to the correct solution. Once you've implemented a brute force solution, it's important to focus on optimization. Look for ways to eliminate redundant operations and use efficient data structures like hash maps or disjoint set unions to bring the time complexity down. During an interview, don't forget to clearly explain your thought process. When transitioning from brute force to an optimized solution, emphasize why the change is necessary and how it improves performance. This demonstrates both your problem-solving skills and your ability to communicate effectively. To deepen your understanding of this problem, it's helpful to explore related problems that share similar concepts. For instance, LeetCode 200, number of islands, and LeetCode 547, number of provinces, both involve identifying connected components in a grid or graph. LeetCode 399, evaluate division, uses graph traversal in a different context but is still relevant. These problems reinforce the patterns of graph-based thinking and can help you build transferable skills. Now, let's consider alternative approaches to solving the problem. Using DFS or BFS, you can explore all stones connected in the same row or column. By counting the number of connected components, you can calculate the removable stones as the total number of stones minus the number of components. This approach is often easier to implement, but it may be slower for larger grids due to the overhead of maintaining stacks or queues. Another option is union find. This method treats rows and columns as nodes and performs union operations for stones that share the same row or column. When optimized with path compression and union by rank, union find achieves a nearly linear time complexity, making it more efficient for larger problems. However, it requires careful implementation to avoid common pitfalls. An additional approach to consider is matrix compression. Instead of treating the grid as a graph, you can compress rows and columns into unique identifiers. This pre-processing step minimizes space usage by reducing the memory overhead associated with explicitly representing the grid. While matrix compression adds complexity to the initial setup, it can be particularly useful in scenarios where memory constraints are a concern. This method highlights the importance of tailoring your solution to the specific requirements of the problem. By exploring these techniques, you can choose the one that best balances simplicity, efficiency, and scalability for the given constraints. Great job! We've reviewed the key points of solving this graph problem efficiently. Remember the importance of mastering DFS and union find for similar challenges. Thanks for watching, like, share, and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!